Now we're going to talk about some important logic blocks that we use when we're designing logic systems. So these aren't individual gates, they're higher level components that we can put together to build systems. The most important ones are multiplexers and demultiplexers, or muxes and demuxes. And what a multiplexer does is it chooses one of multiple inputs. So here's a picture of it, and what you see is we've got two inputs and an output and a select. And the select chooses which of the inputs go to the output. This is essential for routing signals. So if you have different things hooked up on a chip, you need to be able to choose which inputs go to which output. Demultiplexers are simply the opposite of muxes. They're going to take one input and route it to one of many possible outputs. One thing that's worth covering here is the concept of buses. So in the pictures we've been looking at so far, each line represented one bit of data. But when you talk about muxes and demuxes, the inputs usually represent many bits of data, or a bus. So in the example here, that in could have 8 wires, could have 8 values, and then the out will also have 8 values. So when we draw muxes or we draw those things, or demuxes, the number of wires that are going into them depends on the size of the bus. But the behavior is the same. If you have an 8-bit bus going in or one wire going in, the mux is still going to select which input goes to the output. Another common logic block are decoders and encoders. So a decoder is going to convert from a binary set of bits into a one-hot output. For example, if I have the binary value 2, 1, 0, it's going to convert it into having output number 2 turned on and all the other outputs turned off. So we can take a look at an example here. Here's a 3 to 8 decoder. We have 3 binary inputs and then we have 8 one-hot outputs. And here's the logic for that. You can see here if we have a 1 and 0 coming in, so we're going to select input 1, 0, we can see exactly which one gets selected here. This is 2, and here we've selected output number 2. And you can see the logic that's used to generate those outputs. And that logic you can derive yourself just using a Carnot map. Encoders go the other way around. They convert from a one-hot to a binary value. So if I had the one-hot value 0, 0, 0, 0, 0, 0, 1, 0, that's going to tell me it's binary output 1. And why is that? Well, because it's the first place in the input that's hot. This is the 0th place. So we can look at that circuit. And it looks the opposite way around. You have a whole bunch of one-hot inputs and a binary output. And here's the logic for calculating that, and you can see the equations for each one of the output values. Now there's something a little weird about this circuit. If you look at it, D0 is not connected. So what should the output of this circuit be if the input D0 is high? So that would be an input where the 0 bit is high, and then you want to output a binary 0. So a binary 0 is all zeros, so we don't actually use that in generating the logic. Now let's talk about building memories. So memories are 2D arrays of cells, and each of the cells stores one bit of data in it. We enable a whole row of the memory when we're reading out data. So we read out data in a chunk, which is often a word wide. And we can only access one row at a time because they share the same output. So if we look at what we have here, we have one hot row enables. So that is, we can only enable one row at a time. And when we do, we're going to read out the whole width of the array. So if we access this one right here, we enable this row, it's going to activate this entire row in the memory, and all of that data is going to come out. In the example here, that's going to be 16 bits of data output. So how do we build this into something we can actually use? And in particular, we want to use a binary address to access our memory. Remember, when we're doing MIPS programming, our addresses are binary. They're not one-hot addresses. And we also want our data back in bytes. I don't want 16 bits at a time, I want 8 bits at a time. So let's see how we can use those encoders and decoders and muxes and demuxes to make this work. So the first thing we're going to do is we have a 4-bit binary address bus. This is where our address goes into the SRAM, and we want to figure out how to use that address to get back the correct 8-bit chunk of data. So to select the row, we're going to use a decoder. Remember what a decoder does. It takes a binary input and generates a one-hot output. To select the right half of the data, which byte we should get, well, there are 2 bytes there, and we need to select one or the other of them. So we've got 2 chunks of output data, and we want to select one or the other, so we're going to use a mux. The mux is then going to select one or the other of those 2. So how do we hook this all up? Well, we send some of our bits of our address to the decoder, 3 bits in this case because we have 8 possible rows, and we use 1 bit to go to the mux. So now our address is split between the decoder and the mux. Bits 0 through 2 of our address are going to choose one of the rows in the decoder, and bit 3 is going to select which half of the output we get. So let's see how we read this. You can see in the memory we want to read the value written there in the middle of the memory, and this is for an address of 12. So in binary 12 is 1100, and you can see here that parts of that address is going to go to the decoder and part of it is going to go to the mux. So the decoder gets 100 from the address, and that binary decodes into accessing output 4. So row 4 is activated, the whole row reads out its value, and then we get both of these going into the mux. But now we need to choose the right one for our output. So now we take bit 3 of the address, and that tells the mux which side to use. Should it use input 0 or 1? And we choose the correct one, and we get our output data. So the decoder was using part of the address to select the row, and the mux was using part of the address to select the columns. So that's a sort of simplified view of things. Let's look at how real SRAM arrays work. So this is, for example, the array that's in a cache in a processor. We have all the parts I talked about before, but there are some other circuits that are in there. In particular, you have pre-charge and write drivers at the top, and you have sense amplifiers at the bottom. Let's talk briefly about what these are. So the sense amplifier is there because the transistors in memory arrays are tiny. And when they're tiny, it means they're really weak. So you need to have an amplifier to amplify the output signal to figure out if it's a 1 or 0. And if you look at this, here's one of your teeny little SRAM cells, and it's going to run this whole long wire all the way through your SRAM in order to get its value out. So that tiny little cell has to run a really big wire, and that is slow. It has a weak signal, so use an amplifier to amplify the signal and make it faster. The pre-charge and write drivers, well, when you're going to go read, what these do is they pre-charge the wire to 0.5, to a half. Not to 1, not to 0, but to something right in the middle. And why do they do that? Because then it's easier for this really weak transistor to pull it up just a little bit towards 1 or pull it down just a little bit towards 0, and then the amplifier can figure out the rest. The pre-charge and write drivers also control writing. So if you want to write into a memory array, you set the write drivers to output the values into the array that you want to write, and then you do the same thing as if you were going to read. You activate the row. But now you've got really strong write drivers, and they will push their values into the cell. So for real SRAM arrays, you have pre-charge and write drivers at the top and sense amplifiers at the bottom, but otherwise they look just like what we saw. Let's take a look at an example from ARM. So here's a design for a memory array from ARM, and you can see all the parts we were just talking about. Here's the decoder. You can see the logic at the bottom, and then a lot of wires going up the top in order to activate each of the rows. Here are the pre-charge and write drivers at the top of the array, and at the bottom we have the sense amplifiers. And of course in the middle, this is the actual SRAM array. So as we saw, this looks very much like what we were talking about, and it works in basically the same way that we've outlined. So let's summarize these important building blocks we've talked about. So we talked about muxes and demuxes. These are for routing signals around. We talked about decoders and encoders. These convert between binary representations and one-hot encodings. And we talked about adders, a half adder, which is just A plus B, and then a full adder, which is A plus B plus a carry in. So we saw how to use some of these, in particular the mux and the decoder when we're building a memory array, and we'll see how to use adders in a little bit.